Hello. This will be a demonstration of proposition 4 from book 8 of Euclid's Elements, which tells us to, given as many numbers as we please in least numbers, find the least numbers in continual proportion in the given ratios. That's kind of a confusing enunciation, and that's partly on Euclid. He uses continuous proportion here in a different way than he has in the past few propositions, so we got to be a little bit more careful here. All we're given are three ratios which are in least terms, or simplest terms as we would say nowadays. We're given the ratio of A to B, C to D, and E to F. And the task before us is to find the least numbers in continuous proportion which are in the ratios of A to B, C to D, and E to F. You'll sort of understand why exactly it's confusing how Euclid uses continuous proportion here as we go throughout the prop, because typically, or at least how it's been in the past few propositions, continuous proportion means that each term has the same ratio with the next no matter what term you pick. So like 2 is to 4, just as 4 is to 8, just as 8 is to 16, so on and so on and so forth. And you notice that if you pick any term in that sequence and compare it to the one after it, it'll always be in the same ratio. 2 is in the same ratio with 4, that 4 is to 8, that 8 is into 16. It's all just a 1/2 ratio. But that's not going to be the case for continuous proportion here, so we want to look out for that. We're going to begin by taking the least common multiple of B and C. We're going to call that the number G. So B and C both measure G, and G is the least number which they both measure. Next, we're going to create two numbers H and K, such that as many B's as there are in G, there are as many A's in H, and as many C's as there are in G, there are as many D's in K. So that's how we're going to create the two numbers H and K. We're going to create them in that way. Now, it is either the case that our number E, which was given to us, measures the number K, or it does not. We're first going to deal with the case where it does. If E does measure K, we're going to create one final number, call it L, and L will be made such that as many E's as there are in K, there are as many F's in L. Now, because A is to H, just as B is to G, we get this from the fact that B measures G the same number of times that A measures H. We can just use the definition of proportionality to say that they just are proportional because they measure numbers an equal number of times. So because A is to H, just as B is to G, we can then say alternately by proposition 7.13 that A is to B just as H is to G. So you notice we just swap them, we just alternate them. For the exact same reason, namely 7.13, we can say that C is to D just as G is to K, and E is to F just as K is to L. It's just rather straightforward. Because C measures G the same number of times that D measures K, C is to G just as D is to K, again by the definition of proportionality, definition 7.20. So we can say that C is to G just as D is to K, so we can alternate that and say that C is to D just as G is to K. Again, that's just proposition 7.13. And we do the exact same thing with E, F, K, and L. So what we notice is that our four numbers, H, G, K, and L, are in a sort of continuous proportion where the ratio between each term and the next is always one of our given ratios. So H is to G just as A is to B, G is to K just as C is to D, and K is to L just as E is to F. So we have this sort of quasi-continuous proportion. It's not a continuous proportion in the same way as the previous propositions, but it is sort of like that, in that if you take any term, compare it to the next one, it will always be in one of our given ratios. So H, G, K, and L are in continuous proportion according to our given ratios. Next, we want to prove that these are the least numbers which satisfy this property. They're the least numbers in this continuous proportion according to our given ratios. And we're going to prove this by reductio. If H, G, K, and L are not the least numbers in this continuous proportion according to our given ratios, there will be four other numbers which are also in continuous proportion and are less than h, g, k, and l respectively, so that they will be the least numbers in continuous proportion according to our given ratios. We're going to call them n, o, m, and p. So n will be to o just as a is to b, o will be to m just as c is to d, and m will be to p just as e is to f. So they're in, again, a continuous proportion according to our given ratios, but they will be less than our original numbers h, g, k, and l. Now, because a and b, that ratio is in least terms, and we also know that a is to b just as n is to o. We made n and o in that way, and we know that the least, how do I put this? It's always confusing however Euclid words this, but the point is that the least numbers in a given ratio will measure any other numbers in that same ratio the same number of times, the antecedent, the consequent. So what that would mean for us here is because a is to b just as n is to o, they're in the same ratio, and a to b is in simplest terms, they're the least numbers in that ratio, we can then say that a measures n the same number of times that b measures o. That's just proposition 720. We've seen this maneuver several times by now. So a measures n the same number of times that b measures o. We don't need that whole statement, we just need to know that b does in fact measure o. Now, for the exact same reason, we can prove that the number c measures the number o. Remember, we also made the numbers n, o, m, and p such that c is to d just as o is to n, but remember that our given ratio c to d is in least terms, it is in simplest terms, and so c will measure o the same number of times that d measures m. Again, that whole statement isn't important to us, we just need to know that c does measure o. So now we know that O is measured by both B and C. We proved that in steps 6 and 7 respectively. So it is a common measure, right? Now we know from proposition 735 that if two numbers measure any number, their least common multiple will also measure that same number. Again, that's proposition 735. And so we can say that the least common multiple of B and C also measures the number O. But this is the number g. We made the number g in that way in our first step. So the number g measures the number o. And because the number g measures the number o, the number g obviously has to be less than the number o. But you'll remember that we made our numbers n, o, m, and p such that they are less than our original numbers h, g, k, and l. So g should be greater than o. But we've just proven that it's less than o at the same time. This is a contradiction. This is just absurd. And so we can conclude that the numbers n, o, m, and p simply cannot exist, which means that our four original numbers h, g, k, and l are the least numbers in continuous proportion according to our given ratios a to b, c to d, e to f, because h is to g just as a is to b, g is to k just as c is to d, and k is to l just as e is to f. So we found the least numbers in continuous proportion according to our given ratios, which means we've done that which we set out to do. But you'll remember that all of this is under the stipulation that E measures K. But what if it doesn't? Well, that's what the second part of this video is going to have to be. This proposition goes on for another page about exactly this second scenario. What if E does not, in fact, measure K? Before I move on to that second scenario, I do want to just give a particular example of this just to make it more clear. It at least always helps me to give an example, and I hope it helps you too. So say our given ratios are 2 to 3, 4 to 5, and 5 to 7. Okay? So what we want to do, we want to find four numbers which are in continuous proportion according to our given ratios, such that our first number is to our second number just as 2 is to 3, our second number is to our third just as 4 is to 5, and our third number is to our fourth just as 5 is to 7. We're going to begin this by taking the least common multiple of our numbers b and c. Well, b and c here are 3 and 4. So what's the least common multiple of 3 and 4? Obviously 12. So we just write 12 here. Next, what we do is we make our numbers h and k such that b measures g the same number of times that a measures h. Well, how many times does b measure g? Well, b is 3. How many times does 3 measure 12? 4 times. So what we want to do is we want to take 4 a's and put them into the number h. So 4 a's, well, a here is 2, so our first number here is just going to be 8. Because there are as many a's, there are as many 2's in 8 as there are 3's in 12. We're going to create the number k in a similar way by finding out how many c's there are in g and putting that many d's inside k. So c here, remember, is 4. G here is 12. How many 4's go into 12? Well, that's obviously just 3. So we want to find the number such that there are 3 5's that fit into it. That's just 3 times 5, which is 15. So 15 is our next number. Now you notice here we are in this first case, excuse me, where E measures K. E here being 5 as well, and K here being 15. 5 does measure 15, so we're going to do this first case here. And because we're in the first case, the last thing we're going to do, we're going to make our number L. And L will be made such that there are as many F's in L as there are E's in K. How many E's are in K? Well, how many 5's are in 15? Remember, 5 is E, 15 is K. How many 5's are in 15? Well, that's 3. So we want to make a number such that there are 3 7's that fit inside it. Well, that's just 3 times 7. So we're going to put a big 21 here, and this will be the numbers we're looking for. These will be the least numbers in continuous proportion according to our given ratios. Because remember, our given ratios are 2 to 3, 4 to 5, 5 to 7. And we wanted to make a series of numbers which are the least in continuous proportion according to these ratios. That is, that the first term is to the second just as 2 is to 3. The second is to the third just as 4 is to 5. And the third is to the fourth just as 5 is to 7. Have we done that here? Well, 8 is to 12 just as 2 is to 3. That checks out. 12 is to 15 just as 4 is to 5. That also checks out. And 15 is to 21 just as 5 is to 7. It also checks out. So we see that this proposition works, and we can prove that these are the least numbers in this continuous proportion according to our given ratios. That's all I've got to say about this first part of the proposition. I can already tell this is going to be a long video. This first part's already 12 minutes. So I'll move on to the second case, and I'll see you there. Okay, so now let's deal with that second case where E does not measure K. If E does not measure K, we're going to make the least common multiple of E and K, call that M. So M will be the least common multiple of E and K. We can, of course, find M just by proposition 734. Next, we're going to create two numbers N and O, such that there are as many H's in N as there are K's in M, and likewise, there are as many G's in O as there are K's in M. And the final step we're going to do is we're going to create the number P such that there are as many F's in P as there are E's in M. Now, because there are as many H's in N as there are G's in O, we can then say that they're proportional. Of course, just definition of proportionality, definition 720. So H is to N just as G is to O. What we're going to do next is we're going to alternate this proportion by proposition 713 and say also that H is to G, just as N is to O. But you'll remember that in our third step, we prove that H is to G just as A is to B. So we have two ratios which are the same with the same ratio, property of numbers are the same as one another, so that A is to B, just as N is to O. And we can likewise prove that C is to D just as O is to M, and that E is to F just as N is to P. So what we have here are four numbers N, O, M, P, which are in a quasi-continuous proportion according to our given ratios of A to B, C to D, and E to F. Well, remember what exactly this means is that the first term is to the second term just as A is to B. The second is to the third, just as C is to D, and the third is to the fourth, just as E is to F. And we have that exact situation here with N, O, M, and P. N is to O, and our first term is to our second term O, just as A is to B. O, our second term, is to our third term M, just as C is to D. And M, our third term, is to our fourth and final term P, just as E is to F. So we can say that the four numbers N, O, M, P are in a continuous proportion according to our given ratios. Next, we want to prove that these are the least numbers in this continuous proportion according to our given ratios. For if they are not the least, then there will be four numbers which are less than NOMP and which also form a continuous proportion according to our given ratios. We're going to call these numbers Q, R, S, and T. So Q, R, S, and T will be less than N, O, M, and P respectively, and they will be in a continuous proportion according to our given ratios, so that Q is to R just as A is to B, R is to S just as C is to D, and S is to T just as E is to F. You'll remember that we were given not only the ratio A to B, but that the ratio of A to B is in least terms. It is in simplest terms. And we know that the numbers which are the least in a given ratio measure any other numbers in that same ratio the same number of times. Now we know that A is to B just as Q is to R. So we can say by proposition 720 that A measures Q the same number of times that B measures R. We've seen this before. Not all of that statement is important to us. We just care about the fact that B measures R at all. In a similar way, we can prove that the number C measures the number R because C is to D just as R is to S. C to D is in least terms, so C is going to measure R the same number of times that D measures S. We don't care about all that though. We just want to know that C measures R at all. So we can safely say that our two numbers B and C measure the same number R. R is a common multiple of B and C. And we know by proposition 735 that if two numbers measure any other number, their least common multiple will also measure the same. So that because B and C both measure R, their least common multiple, the least common multiple of B and C, will also measure R. But you remember, the first thing we did in this entire proposition is make the least common multiple of B and C, and we called it G. So G will therefore measure R. Next, because G is to O, just as K is to M, remember we made O in that way, we can alternate this proportion by proposition 713 and say that G is to K, just as O is to M, so that because O is to M, just as R is to S, we know this is true because we made R and S that way. We therefore have two ratios which are the same, with the same ratio, property of numbers, they're the same with one another, so that we can say that G is to K just as R is to S. And the last thing we're going to do in this step is we're going to alternate that once more again by proposition 713 and say that G is to R just as K is to S. Why do we care about that? We care about that because G measures R. And because G is to R just as K is to S and G measures R, we can therefore say by the definition of proportionality that K also measures S. But we know that the number E also measures the number S. How exactly we know this, Euclid doesn't make clear, but it follows the same sort of logic as steps 14 and 15, right? So we know that S is to T just as E is to F. We know E and F are in least terms. Those are the least numbers which have that ratio. And we know by proposition 720 that the least numbers of any ratio measure any other numbers which are in the same ratio at the same number of times. So E is going to measure S the same number of times that F measures T. We don't care about that at all. We just want to know that E measures S at all. So yeah, we know E measures S, but we've just proven that K also measures S. And we know, again, by proposition 735, that if two numbers measure any other number, their least common multiple will also measure the same. So the least common multiple of E and K will also measure S. But remember, we made M as the least common multiple of E and K. So the number M measures the number S, which of course implies that the number M is less than the number S. But this is contrary to how we made the number S. We made the number S specifically to be less than the number M. So M has to be both greater than S and less than S, which is just impossible. So we can safely say that there are no numbers less than N, O, M, and P, which form a continuous proportion according to our given ratios of A to B, C to D, and E to F, which means we've done all that we set out to do. We wanted to find the least numbers which are in a continuous proportion in our given ratios A to B, C to D, and E to F, and we've just done that. So we're done with the proposition Q, E, F. Again, before I close out the video, I would just like to give a particular example of what this might look like in the second case specifically. So say instead of having the ratios 2 to 3, 4 to 5, and 5 to 7, like last time, we're going to have 2 to 3, 4 to 5, and 6 to 7. So we're going to have 2, 3, 4 to 5, and 6 to 7. Okay, so say we wanted to make the continuous proportion, or find the least numbers in a continuous proportion according to our given ratios. Well, we're going to repeat a lot of what we did in the first part. We're going to make the numbers 8, 12, and 15. I'm not going to go over how exactly you get those numbers. You can just, play back the video. It's kind of what video is for. But we're not going to stop there, because what we realize is that 6, which is E in this case, does not measure 15, which is K in this case. So we're bumped to this second scenario of the proposition, where we have to do a little bit more work. Now, our first step is to take the least common multiple of 6 and 15. That turns out to be 30. So I'm going to just pop a 30 right there. Our next step will be to create our numbers n and o such that there are as many h's in n as there are k's in m, and likewise there are as many g's in o as there are k's in m. Okay, how many k's are in m? Well, our k here is 15, and our m here is 30. How many 15s are in 30? Well, that's 2. So we want to make a number such that there are 2 h's in it. What's our h? Our h is 8. So twice 8 is just 16. There are 2 8s that fit inside 16. So we can put a 16 on the front there. And we can do a similar thing with O. So G here is 12. So we want to do twice 12. We want to find the number that is just 2 12s. That's 24. So we're going to plot that right here. Now, of course, we have to create the final number by making the number P. And we made the number P such that there are as many F's in P as there are E's in M. Okay, what's our E here? Our E here is 6. Our M here is 30. How many 6's are in 30? Well, that's 5. So we want to make the number with 7 5s. 7 times 5 is 35. So our continuous proportion, quasi-continuous proportion, will be 16, 24, 30, and 35. These will be the least numbers in a continuous proportion according to our ratios 2 to 3, 4 to 5, 6 to 7. This is pretty easy to verify. 16 is to 24, just as 2 is to 3. 24 is to 30, just as 4 is to 5. And 30 is to 35, just as 6 is to 7. And we can prove that these are the least numbers that satisfy this sort of continuous proportion. So with that, Proposition 8.4 has come to a close. Long one. I'm sure you've realized by now. Kind of an annoying one, but you gotta bite the bullet sometimes, and I had to make this video sooner or later, so I hope you got a lot out of it. This is kind of confusing and windy and just not a very clear or transparent proposition, so I hope I've made it easier for you to understand. If I failed at this, you can just comment and I'll likely answer. That's all I've got to say about this proposition, and this video. So I'll end the video here and move on to Proposition 8.5.